V yet.
It might be.
This is the last test, so let's finish it out. Not going to final.
What?
Oh, I didn't say anything. No final.
So
Yeah, here's the drops for final.
Okay, so this test is V&M diagrams, shear stress, and bending moment. Is that right? Like M is sigma is my over I, and tau is V Q over IT. Is that essentially the topics that we're going over for this test? Okay, cool. So yeah, I'm going to go over my test from last semester and spout bouts of wisdom as I go. People on that side, what is the farthest you can see? That's crazy talk, right? Here? Okay. And same on this side. What's the farthest you guys can see on this board? Too far. Good. Okay. We'll make that work. Okay. So let's jump into it. This one shouldn't take as long as test 3. This stuff isn't nearly as hard. How did test 3 go, by the way, in general? All right, better than test 2 at least? I heard test 2 was a nightmare. Okay. Mixed bag. That's fine. All right. So problem 1, pretty standard. We're just drawing a V&M diagram. So they're giving you a frame with forces, moments, all sorts of stuff on it. They want you to draw the V&M diagrams. So that's the actual beam. So I'll start with the free body diagram. We have a kilonewton load coming down on the left. Also, it was very nice for them. Normally, the first step would have been solve for the reactions at the pin and the roller, but they gave it to you just to save the steps because you guys have done that 10,000 times by now. So they gave you the 0.5 kilonewtons and the 3.5 kilonewtons at the supports. So we have 0.5 kilonewtons at the roller. We also have an 8 kilonewton times meter moment acting at that same spot. Another 1 kilonewton force. This is all, I'm just redrawing the one up there. I'm just to have it on the whiteboard. .5 kilonewtons at the pin, and we also have a distributed load of 1 kilonewton per meter on the edge. And 2 meter, 4 meter, 4 meter, 2 meter. Okay, so that's essentially everything that you guys already see up there. So when doing it, you could just go straight down for each point when you're drawing the V&M diagram. So you always do the V first. V is your shear force. Okay. So the first thing you'll start to, so the first thing we're going to use are the forces. So We have a 1 kilonewton force acting on the beam on the left, so we go down 1 kilonewton on the V diagram. -1 because it's down. If it was aiming up, we would go to +1 on the V diagram. That's pretty self-explanatory. In between any forces on the beam, so as I'm going from here to here, since there's no force acting along it, there's no distributed load or anything, when you go from one point to the next, the value on the V diagram stays the same. So we stay at -1 until we get the next external force on it, which is the 0.5 kilonewtons. 0.5 kilonewtons acting up, goes straight onto the V diagram. Positive 0.5. We don't care about this moment yet. Any moment acting directly on the beam, we're not going to deal with until we get to the M diagram, so we can ignore that for the time being. So we went up 0.5, so now we went from -1 to -0.5. Again, there's nothing happening in between the 0.5 kilonewton load at the roller and the 1 kilonewton load acting to the top. So we stay constant at -0.5 until we get to that force. 1 kilonewton down, we drop from -0.5 to -1.5. Everything stays the same. The first thing we have here is a 3.5 kilonewton load going up, which brings us from -1.5 plus 3.5 is +2. So is everybody good so far with what just the concentrated loads do to the V diagram? I'll get to the distributed load in a second. Is everybody good with the concentrated loads? Okay. For the distributed load, since it's working over a distance, not, oh, I didn't actually write the value, 1 kilonewton per meter. Exactly. Instead of it acting at one point, it's going to change gradually over the course of that distance. So you're working 1 kilonewton per meter times the 2 meters that it's acting across comes out to a total. Remember, if you remember from test 3, I don't know if it was on the test, but I did it at the review for whoever was here. For normal distributed load, you're always going to have, it's just going to be equal to the length that it's acting across times this value. I think it was called W. So the total change is going to be the 2 meters times the 1 kilonewton per meter, which is, it's acting down, so -2. So by the time it gets to the end of the 2 meter mark, it's -2 in a straight line. So all of these show how you're using the concentrated loads, and this slant is the distributed load. Any questions on that? Cool. Okay, a couple things to note with this. On the V diagram, you're always going to finish at 0. After everything goes into it, you should always finish at 0. If you didn't, go back, check your work, you did something wrong. I mentioned already the values will not change in between any external forces acting on the beam. And I also mentioned the moment isn't going to affect anything on the V diagram. Is everybody cool with the V diagram? Okay. Oh, important thing. Make sure you make it obvious what's corresponding to what. So for me, I just put dotted lines, which is why I always did it directly under. So just to show, okay, this is from the 1 kilonewton force. This corresponds to that, to here, and to here. And then do the same thing with the actual load. So this is 2 kilonewtons. This is -0.5. This is -1.5. That way there's no ambiguity. Next is the M diagram. I'll just do a quick sketch of it. So the V diagram is in kilonewtons because it's a force. This is a bending moment, so it's kilonewtons times meter are your units, or some other force times distance. So now we're going to take everything we took from, I'm going to be doing a little bit of back and forth. We're going to take our values in the V diagram to help us with the moment. So everything we did here, we're going to use the areas from under this curve to find the values that it's going to change in the M diagram. So what that means is the area under this section is -1 times 2 meters. So that's -2. This is 4 meters times -0.5. So that's also -2. This is 4 meters times -1.5, which is -10, I think. Wait, that's actually not right. 6. Sorry, can't do math. 1.5. Yeah, okay, cool. And the area under this part of the curve is 2 meters times 2 meters cut in half. 2 meters times 2 newtons, sorry, kilonewtons. This is +2. So these are your areas, and since we multiplied, this is corresponds to -2 kilonewton time meters, -2 kilonewton time meters. That's the unit for all of these. So how that helps us is now we go to the moment diagram. So the first thing we did is -2. So that straight line is going to become, first axes, 0, 2, 4, 6, -2, -4, -6. So we found that -2, so it's going to drop -2 kilonewtons times meters across that 2 meter span on the beam. Next, that moment that we ignored a second ago, that's a +8 kilonewton meter. You know it's positive because the sign convention for bending moment is that. So since it's going clockwise, counterintuitive to how you've been doing everything so far, now that it's clockwise, this is positive. So after that first step, you're now going to include that 8 kilonewtons times meters, and you're just going to go straight up 8 on your M diagram. Has everybody gotten that? And then we're going to continue everything else the same way. So we have another -2 kilonewtons times meters that's going to span across 4 meters now. So by the time we get to the next force, we drop 2 from 6 to 4. And then we're going to drop another 6 from 4 to -2. The last thing we have now is turning that slanted line into something on the M diagram. So the same way any constant on the V diagram became a slant, became a slope on the M diagram, that slope on the V diagram is going to become a parabola on this. So we said it was +2, so we're going to go up a total of +2, but instead of going in a straight line, it's going to be arced. And if I actually had a full piece of test paper in it and not short whiteboards, I would have drawn the M diagram directly under that V diagram, and I would show this corresponds to the force above it, this corresponds to the force above it. But does everybody see what connects to what over there? This curve here, it's important to note, the way I knew it went up +2 because of the area under the slope there. But the way I knew it went like this and not like this was the slope of that line. When the slope on the V diagram is negative, it's concave down. When the slope on that line is positive, it's concave up, which is how I was able to get this slope here. Does anybody have any questions on the M diagram? Yes. So the -2 area that I found under there is a moment. So that's the change in moment across that distance. So you'll see here my change in moment was -2. I dropped from 0 to -2. But that's the thing. That -2 is the total amount the moment is going to drop across this 2 meters. So that -2, you could think of it divided by that 2 meters. It's actually only a slope of 1 on the moment diagram, the same way here. It's also a drop of only -2, but across 4 meters, which is why it wasn't quite as sloped. But this is the total amount of change. This is the total moment change. Do you get that? Cool. Any other questions on that? Okay. Now, okay. Couple things to note about the moment diagram. Similar to the V diagram, you have to finish at 0. Again, if you didn't finish at 0, you did something incorrectly. The areas from the V diagram are what are going to denote the changes in moment. And be careful to make sure that your slope matches the concavity. So a negative slope is concave down, positive slope is concave up. And then don't forget that this is your sign convention, and it's pretty different than what you had seen up until now. So that's it for these. Any questions on V&M diagrams? Yes.
You define the x value when the line crosses.
No, you don't have to necessarily define that point, but what I would do, and thank you for noting it, is the exact same thing that I did on the V diagram, just kind of note what corresponds to what value, and again, bring this back up to the V diagram and say where it hits, but you don't have to like find that value specifically. Okay, so that was it for V&M diagrams. We'll jump into question 2. Which is bending moment. Can you pass that around for me? Thanks. Okay. Yes. Which one? That 8 kilonewton over here? I didn't. Oh, yeah. On this one, I added it because I said the sign convention for when you're doing these problems is the sign convention for bending moment. Is this is your positive moment. So since it's going clockwise over there, it acts positive, so it went up 8. So then that just goes straight onto this graph. Kind of the same way the forces went straight into the V diagram, the moments go straight into the M diagram, and it's just an immediate change. Okay. So, question 2, they were nice. They drew the V and M diagrams out. Well, they were nice to us. Mostly because we had just proven that we could draw V and M diagrams. So, they gave us a figure. They gave us the length diagram, and they gave us a cross-sectional area. And I believe they asked for Yeah, they want the maximum bending stresses. So your bending stress is that sigma value. And unlike test 2 where we did sigma is force divided by area, now we're doing sigma is equal to negative my over I. That's the new formula. So the y value and the I value you're going to get from the cross section on the right, and then the moment value you're going to get from the M diagram down here. So a possible thing they might have you do is actually go through the V and M diagrams and then do something like this, because you need to have done the M graph to see what the maximum moment's going to be. But we'll go through that step by step. So the first part was just find the moment of inertia about the neutral axis, which they told you is right here along this line. So to do, oh, yes. It will. But when we get to part B, I'll show you where the negatives start to cancel each other out. But the equation does have, you have to include the negative as part of the equation. You haven't done this. Who's your professor? Equation's positive. Interesting. Williams has a negative. Of course they do, because why would they agree on anything? Okay. That's fine. I'll show you why you have positive and negative moments and where it comes from, and then we'll go through it. If your professor has you do it one way and you're comfortable with it, then that's fine. I'm going to show you a way that will 100% work with a negative my over I. So if you're not comfortable and you want to use mine, go nuts. But it's up to you guys. It's one of those things where you could do a negative down, a positive, and everything cancels itself out if you do it correctly. But okay, so the first part, find moment of inertia about the neutral axis. So the first thing I did was I split this cross section up into two different shapes. I took the rectangle on the bottom and the rectangle on the top. I wanted the centroid of each one. It's pretty simple. Since it's a rectangle, it's just cut it in half. So this is 4 inches, so the centroid is 2 inches across, and this is 3 inches, so it's 1.5 inches up. And then for the tall, skinny one, it's again 2 inches across, and now this is 6 inches, so we cut it in half. So this is 3 inches from the normal axis to the centroid of that shape, plus this 3, because I treated it like a coordinate just to make my life easier. So we said that it was 6 inches away from the bottom. So I just wrote out that math quickly. The centroid of A1 was at 4/2, 3/2, which was 2, 1.5 on that coordinate plane I made up. And A2 was at also 4/2, and then 3 plus 6/2. I don't think you actually have to work out this math because visually it's very obvious what's going on. So if you just write where it is, you're fine. But just to be safe, I threw every step of it on the paper. So those are the locations of the two individual centroids that we're working with, the fat one, the shorter one on the bottom, and the taller one on the top. And then the areas of those were 4 inches times 3 inches is 12 inches squared. And the bottom one, oh, that was actually the bottom one. And then the top one, 1 inch times 6 inch is 6 inches squared. So to solve for moment of inertia about the normal axis, we're going to use parallel axis theorem from the last set of lessons. So moment of inertia about the normal axis. I'm adding a summation sign just because there's going to be more than one thing compounded together. The summation of the individual moment of inertias plus AD squared, which is going to take the moment of inertia from the centroidal line of each shape and correspond it to what it will be on the neutral axis that we're working with. So what this turns into, you have 1/12 base times height cubed, which is the equation that they'll give you, but you've probably seen before for moment of inertia of a rectangle. So 1/12 base of, we'll do the bottom one first, so 4 inches times 3 inches cubed plus AD squared. The area of the bottom one is 12 inches squared times that distance. That distance is from the centroid of the part we're evaluating, which is down here, to the normal axis that we want to focus on. So that distance is 1.5 inches. Does everybody see that? Does anybody not? Okay. So that was me using parallel axis theorem for the bottom shape, and now I'm going to do it again for the top one. So again, it's a rectangle, so 1/12 base height cubed, so 1 inch for the base, 6 inches for the height, cubed plus the area of the top guy was 6 inches squared, times the distance from its centroid, which is halfway up, to the normal axis is 3 inches. And when you do it all together, plug in the numbers, it does come out to 108 inches to the fourth. So that was part A. Does anybody have any questions on how I found the moment of inertia or how I used the parallel axis theorem? No. Okay, cool. Part B. So before I start getting into the math, I'm just going to give you a little bit of a lesson on, did either Billa or Williams explain to you how you're going to get 4 equations for this? There's 4 different bending moments. So for the m value in that my over I, one of 2 things can happen. Your moment can be positive, or your moment can be negative. At any point across a beam or a shape or whatever fixture you're dealing with, your moment will be positive or negative. If the moment is positive, because of the sign convention, which we said looks like this. If you have a positive moment, the top of the shape is under compression because you're pushing it in, and the bottom of the shape is under tension because it's getting stressed out. Does everybody see how that happens here? So when the moment is positive, you have the top under compression and the bottom under tension. And you'll see why this is important when you actually go to make the 4 equations. When the moment is negative, you have the opposite of this. So instead, you get the top under tension and the bottom under compression. So when the moment is negative, the top is under tension, the bottom is under compression. So this is ultimately going to give you 4 different equations. You're going to have an equation, 2 equations measuring to the normal axis from the top. One where it's under compression, one where it's under tension, and then same thing from the bottom, one where it's under compression and one where it's under tension. So let's go to write out the 4 equations. Does everybody understand that or have questions on the sign convention or why there's 4 equations? I should know why there's 4 equations. Everybody get here? Everybody copy all this? So we'll just go through them one by one. So the first one I did measured from the top when it's under, measured from the top when the top is under compression. So we're solving for the bending moment now, or the stress is due to the bending moment. So that's sigma. When the top is under compression. So the formula that Billa always taught me was negative my over I. You said Billa taught you positive? That's what, the my over I? Which one? Oh, that's really weird. Okay. The 4 equations is important because it's part of how you actually solve for the maximum stresses. What's the farthest topic you guys have gotten to? So, what is that? Nah, that's, you'll get to that for the final. So to find the max, so the reason you do 4 equations, I said 2 of them show something under compression and 2 of them show something under tension. So they want the maximum tensile and compressive stresses. So you're going to end up with 2 answers, 1 in tension and 1 in compression. When you do all 4 equations, you'll get 2 for tension, 2 for compression, and you compare them and you just take the highest value. So, but you need both to compare to see which one is the highest. So I don't know why he wouldn't have gone over, guys in Williams' class, did he like, with Fontaine you did multiple also, okay, that's fine. That's really where the Billa dropped the ball on that one then. Either way, it's not super complicated, so I can walk you through it and show you why you're doing it and how it works. So the first one is the top is under compression. So your formula is negative my over I. So, okay. When the top is under compression, we're going to go back over here, the moment is positive, right? So he skipped a couple steps. So you draw a V diagram, you draw an M diagram. 1265 pounds times feet is your maximum positive moment, and negative 2250 pounds times feet is your maximum negative moment. So since the moment is positive when the top is under compression, we're going to use the positive moment here. So negative stays. The moment is positive 1265 pounds times feet. You're measuring to the top. So the y value is the distance from the normal axis to the top of the figure. So in this case, it's 6 inches. Divided by the 108 inches to the fourth that we just found. Another thing that they might throw in there just to trick you, this figure, everything is done in pounds feet, and everything there is done in inches. So you have to go in the numerator and multiply by 12 inches per foot, just to keep the units consistent. And when you evaluate that, you get negative 843.33 psi in compression. So we said the top was under compression, so the value came out negative because of it. Okay, a lot of questions. Sam. So the y in negative my over I is the distance from the neutral axis, or I guess wherever they ask you to work with. In this case, the maximum is always going to be at the neutral axis for anything. So 6 was the distance from the neutral axis to the top, which is where we were looking, because the top was under compression. If you were going to the bottom, it would be 3, because that's the distance from the neutral axis to the bottom of the figure. I saw there. Yes.
We're here to 12:55.
Okay, so I said that when the top is under compression, the moment, it's because the moment is positive. Are you good with everything on that side of the board? So the positive moment, I had a maximum positive and a maximum negative. The maximum positive moment was 1265. That was given. And if you had actually gone through the steps of drawing the Vietnam diagrams, you would have found that.
Oh, okay. So you have to do this first.
Yes, but I mean, for the sake of saving time, there's a good chance they'll just give it to you. So that's where we took the 1265 from. Yes. 12 inches. So I left this guy as pounds per square inch. So this inches per feet, I'm actually canceling out that feet with that feet, and it's leaving me with 2 inches in the numerator. Sorry, 4 inches in the denominator, which is how I got pounds per square inch. So from a unit standpoint, pounds times feet times inches, right? Times inches per feet, which I did, divided by inches to the fourth. Feet and feet cancel out. That inch in the numerator and that inch in the numerator turn this inches in to the fourth to inches squared, and now you have pounds per inches squared, which is just psi. So that's why I did it that way. You technically also could have done it the other way and canceled out inches and left the final answer in pounds times feet. But for that, I think you would have had to change this 108 inch to the fourth to some feet to the fourth, which is an annoying conversion because it's 12. You'd have to multiply it by like 1 over 12 to the fourth. So this was just the easier conversion. So do you understand why I did that? Cool. Any other questions so far? At least on this first one. Yes.
So I got the answer positive because like Phyllis told us not to worry about signs. But like I got positive and I put compression. Would that be right? Like I still
Yeah, because you know it's under compression because you're dealing from the top. So yeah, conceptually, there's a lot of different ways to think about it because this is a combination of 4 things. So in my head, I conceptualize it first as the moment is positive or negative, and then I break it down this way. You could start with compression and tension and then say, okay, I have positive moment top, positive moment bottom. Either way, you're ending up with 4 equations. But the reason I do it that way is because I know that I can trust that formula to work. If you found a way to use the positive my over I and like not include a negative that I included somewhere and it comes out to the right answer and you know to do it, then that's totally fine. Do that on the test. This is the way I was taught to do it by Billa, and it always worked for me, which is why like I trust this equation if you input everything correctly. But if you have something that you're more confident with, it's 100%, and Billa says it's cool, then 100% go with that. Yes? The 6 inches for y is the distance from the normal axis to the top, since we said we were evaluating the top under compression. So it was just that distance up. Anything else on this first part? No. Okay, so we'll do the next of the 4. So the next one I had was bottom under tension. So bottom under tension, I think that was the second one on the list over there. Yeah, bottom under tension. Again, the moment is still going to be positive because we're still in this first category of how it works. So 2 of the equations come from a positive moment, 2 of the equations come from a negative moment. So now instead of when the top is under compression, the bottom is under tension. The top is squished in, the bottom is stretched out. The equation stays the same. It's negative my over I. Since we're still dealing with the positive moment on the M diagram, we're still going to take this 1265 pounds times feet. But now, since we're evaluating at the bottom, we're looking at the distance from the normal axis to the bottom of the figure, which is only 3 inches. So your y changes to 3 for this part. And we're going to do that same unit conversion, the 12 inches per foot. And your I value stays the same. That's your 108 inches to the fourth that we found in part 1. When you do the math for this, you get 421.67 psi, and now it's in tension. And the other reason I kind of like doing my negatives the way I do here, you'll notice this guy came out negative and he's under compression. This guy came out positive and he's under tension, as most things, just as like a sanity check, that's the way my numbers have always came out. And when I go through the next 2 equations, you'll see the same thing. The negatives are compression and the positives are tension. No, that 3 is, so this is why I said there's a bunch of different ways you could do it, and every way is as equally right as the last. If I got rid of this negative and said, okay, well now my displacement is a negative value, when I do my equations, my y value is always positive every time I do it, because it's the distance from the normal axis to the bottom. So that, yeah. Which one?
Like if you're dividing negative 1 divided by positive 108, I'm going to get a negative.
Dylan, I lied. And yeah, you're right. Yeah, I'm sorry. I didn't copy my old math correctly. It is a negative distance down. And that's how I got the positive tension, yeah. Yep, -3. I can't copy my own math. Sorry, guys. Yeah, so sorry about that. Since you're going down, it is -3 from the neutral axis to the bottom, so you're 100% right. So yeah, does that clear up your thing too? Okay, so yeah, this is -3. The negative cancels out with the negative, so now you get positive. Cool, okay. Anything else for that second one? Okay. So we'll move on to the next one. So now we want the stress due to bending moment when, or top under tension. I'll start with top under tension. When the top is under tension, so negative my over I again. But now, because of the way I justified everything over there, when the top is under tension, your moment is negative. So now we're taking the negative moment off the end diagram since that's the part of the beam that we're evaluating. So for the moment, instead of the 1265, we're now going to use the -2250. So that first negative stays, and now we're also going to add a second negative for the to represent the negative moment. So -2250 pounds times feet times, we're dealing with the top, so we're back to 6 inches again, which is +6, which is the displacement from the normal axis to the top of the cross section. Times 6 inches. Unit conversion again. And moment of inertia again. When you do this, these two negatives cancel out, and like I said, it's under tension, so it's going to be positive. You get positive 1,500 psi. And that part's under tension. That's the third. And the fourth, same way. So now we're doing the bottom under compression. So we'll keep the formula, and just like the third equation, when the bottom is under compression, the moment is negative. So we're going to take this negative value off the M diagram again. So negative, negative. And since we're evaluating at the bottom, we're going to go down from the neutral axis, and now it's -3 inches is your Y value. Times 12 inches per foot over 108 inches to the fourth is, again, negative, negative, negative. So your final value is -750 psi, and that part's under compression, like I said at the beginning. So those are the 4 equations that you do. And those are the 4 combinations of ways you use to get them. And now the reason we did this is they wanted the maximum tensile and compressive stresses due to bending. So we have 2 compressive stresses, and we have 2 tensile stresses. So if we're looking for maximum, you're just going to take the larger of the 2. So stress due to bending for compression, maximum, is the -843.33. since that's the higher magnitude of the two compressive ones. And similarly for tension, you're going to take the 1500 psi one. And that was the final answer for this one. So any questions on anything with this? I know there was a lot of confusion with negatives and this and that. Yes.
For the third one, why is it 6 inches if you're looking at the
So it's 6 inches because we're still evaluating from the top. So anytime we're evaluating from the top, it's 6. Anytime from the bottom, it's -3. The positive and negative moment affects the m value, which we take from here. And then I stays the same. So that's why I said at the beginning, I said, you're going to get your moment of inertia and your y value from the cross section, and you're going to get the moment from the length diagram, or in this case specifically your m diagram. Any more questions on any part of question 2, or this topic in general? Yeah? All right, cool. Jump into question 3 in a sec. Did anybody not finish copying anything on either board? Awesome. Okay. Bring it back, guys. Last problem. Making good time, I think. Oh, wow. Okay, so here's the last one. So the last one we did stress due to the bending moment. So now we're going to have stress, shear stress due to shear force. So the equation for the last one was your my over I. Now you're going to have tau is equal to VQ over IT. That's your equation for this one. So, and similar to that, you're going to get your shear force value from your V diagram, and you're going to get your Q value, your I value, and your T value from the cross-sectional area. So we started this one. He wanted the maximum shear stress in the diving board, 8 points. That was pretty much the whole problem. That part B was like a little something extra on top. So we wanted the maximum shear stress, this tau max. So we needed to find each of the components of the equation. So started with V. So I drew a free body diagram of the length diagram. The actual figure is over there on the right. It's the guy on the diving board. So you have a pin under him at A, a roller, well, you could treat it like a roller because there's just one reaction force going up at B and his force acting down. So there's a reaction, A of X and A of Y, because a pin has two reactions, and you have a B of Y because that roller only has one. And the guy himself exerts a force. He is 78 kilograms times, don't forget to multiply by gravity, 9.81 meters per second squared is 765.18 newtons. So that's the setup for the free body diagram. We just solved through for each of the components. So the first one was the easiest, is summation Fx is 0. The only force acting in the x direction on this body is A of x, A sub x, so A sub x is just 0. Next, I did the moment at A is, I forgot to, well, the lengths are over there. Yeah, 1.5 and 2.5. So you have By is going counterclockwise, so you have positive By times 1.5 meters minus 765.18 newtons times 4 meters to get to A, and that equals 0. And when you do the math, By equals positive 2040.48 newtons. And then with the third equation, summation Fy, A sub y plus 2040.48 minus 765.18 newtons is 0. And A sub y is negative 1275.3 newtons. So that was just solving for the reaction. So now we have values for AY and BY. AX just went away. So now from this, we're going to draw, they didn't give it us this time, so we actually have to draw out the V diagram. That way we can get the V max value for the first part of that equation. So I'm actually going to draw it under this, so make sure you copy that so I can erase it. Everybody grab that? Cool. So V is your force measured in newtons. Drawing the V diagram, the first thing that happens, A sub y, which I just erased, but I said was negative 1275.3 newtons. So the first thing that happens is you go from 0 down. Should use a different color. Should not use a different color. Whatever. Down to negative 1265.3. And just make sure you label all relevant points on your axes. The next thing that happens, it's going to go across to By. At By, it's going to go up. By was positive 2040.48 newtons, so it's just going to go straight up by that amount. And that's going to bring you to a total of 765.18. Which, funny enough, is exactly what this is, so that it comes back down to 0, which is why I said it's always going to finish at 0, because if you get this free body diagram, those three equations to work, and you have non-concordant equilibrium existent, you're always going to finish there. And then just make sure you identify what everything connects to. So there's your V diagram, positive 765.18, negative 1265.3. So for V max, this is actually your V. If we're looking for tau max, we want the maximum of all these values. So V max here, the higher magnitude is the 1265. Yeah, Sam. Negative 1265 point. Negative 1275.3. Sorry. That was when I did the free body diagram in the first part. Negative 1275.3 was A sub y. So this reaction right here is negative 1275.3. I just erased it so that I could draw the graph, but that was negative 1275, and that was 2040.48. So we took that. So our V max is actually a negative number. It's 1275.3 newtons. So that's the first thing that's going to get plugged into that equation. The rest of the stuff is going to come from the cross-sectional area. Any questions on V diagram? Yes? So you're going to see when we come back around later, we're actually going to plug it into this equation as a negative number. And you're going to see it's actually going to turn your tau into a negative value, which is totally fine. The reason we selected it, though, is just because it's the higher magnitude, which is what we care about here. The sign isn't important, but you still need to keep track of it. You can't throw it away. Anything else, or you get to move on? Cool. So we'll do Q next. So Q is your moment of the area. So to find it, Q is equal to, that's your cross-sectional area here. So I'll just draw out a copy of it roughly. With your normal axis somewhere around here. So to find your value for the Q, first you're going to shade one way or the other. So not actually one way or the other. For this problem, we're evaluating at the normal axis. So we're going to shade in either direction. I'm going to go up just because this rectangle is easier to evaluate than all this jagged tooth things down here. It does become important if I was dealing with, say I was dealing with a rectangle and my neutral axis was through the center, but they wanted me to evaluate at some other point, CC up here. Since the centroid of your object is there, you always need to shade away from the neutral axis. So I said here I could have technically evaluated on the bottom half and dealt with all this, but I chose to go up. I was given a choice since I'm working at the neutral axis here. I can't shade in the direction of that centroid. I would have to shade away from it. So if they give you one where you have to evaluate at a separate point, just remember that you have to shade in that direction. So that brings us back to what the actual value for Q is. It's the area of that shaded region from the line you're evaluating at to either the top or the bottom. Times the distance from the center of that shaded. Give me one sec. The distance from the centroid of that the center of that shaded area to the surface you're evaluating at. So we'll just call this y for the sake of it, and then we'll just plug y into that equation. So that's your formula for Q. 1284. Okay, cool. So does anybody have any questions about that part? So when I actually go to plug it into the values I'm using now, what was that?
So what is the formula for that? For like, how should we know that the area of shade is? Yeah. What if they don't?
So I shaded that region myself. So I knew where the normal axis was, and I shaded in either direction and found the area of it. Because we know because that's the cross section, right? So we know the general definition of Q is this. It's the area of whatever region you just shaded times the distance from its center to the surface. So it's written as like, I think the actual equation that he's going to give you in the, like, for the answer sheet on the test is, the way it's actually written is Q is equal to y bar times A. So A was that area, Y was that distance. But this is exactly what it is in the answer key, in the formula sheet. So when you actually go to plug it in, the area of that is the 350 millimeters, so 0.35 meters times 0.012. I just put everything back to meters to make it easier, but just be careful because they gave you that value in millimeters, so just change it back. 0.35 times this is your area times the distance from the center to the edge is 0.012848 meters divided by 2, because that's the distance from the center to the edge. Does everybody see how I got these two? Yeah.
How did you, like, so how do you know that you're, like, given, like, which way to shade? Like, you chose the top part, but, like,
So
how you shade the bottom part?
no, so that's why with this rectangle I was showing you, in this question we're evaluating at about the normal we're evaluating about that NA line, which they gave us in this situation. And when you're evaluating at that line, you have the liberty to go in either direction. But again, if this is your rectangle, that's your normal line, and you're evaluating at some other point here, you have to shade away from the line. So in this case, I'm forced to shade up, and if I was dealing with a line down here, I'm forced to shade down.
So because they just say evaluate at the normal axis,
Yes,
you're able to.
I was able to pick. For this question, it just makes significantly more sense to work in that direction because the shape up is just a rectangle and the shape down is 4 rectangles or that minus 2 others. It's more complicated, it would have been more work. I would have found the same thing at the end of the day, but it would have taken me 3 times as long. So I plugged in all the numbers for Q, and you have 28.89 E negative 6 meters. The units is meters cubed. So does anybody have any questions on how I solved for Q? Okay. So now we have 2 of the 4 things that we need for the equation. We found V, we found Q. Now we need I and T. I'll say I. So they were nice. They gave us I for this one. It's in the equation. It says I is 7.9925 10 to the negative 7. So that's the third. And your thickness, that T value is thickness. It's whatever the thickness is at the point you're evaluating. So in this case, we're evaluating the normal axis. So the thickness is from here to here. That one's pretty straight across. So I doubt I'll give you an example like it, and I'm just saying this from memory, but I recall that if for some reason you were evaluating down here and you needed the thickness across a spot with some spots filled in and some spots not filled in, it would just be 10 plus 10 plus 10, or you could do 350 minus those empty boxes to find the thickness at that height. But for this one, it's just the 350 across. So now we have the four variables, so now we can just plug it back in to solve for tau. So the maximum tau is the maximum shear force times Q times, it's going to be I at the normal axis. It gave us I and A, but like I said in the last question, whenever you're dealing with maximums, you're dealing with things at the normal axis. So we know we're using that one. And thickness. So again, I said before, it didn't matter that it's a negative, but we still need to keep the negative with it. So negative 1275.3 newtons times the Q, 28.89 times 10 to the negative 6 meters cubed, divided by 7.9925 times 10 to the negative 7 meters to the fourth times 0.35 meters. And now you can see why I had everything as like 10 to the negatives, but everything in meters, because now when we come back to this, everything's in meters and we don't have to do any more unit conversion. And this equals, because of this negative shear force, we're going to get a negative shear stress, negative 131.71 kilopascals. And part B was just asking for the location. So the location is, if you remember from the V diagram, when we were in between A and B, we had the negative, I'll redraw it, since we're actually going to need it for this. It looked roughly like this. This was the higher magnitude value, so we know that the maximum shear stress for answering part B for where it's located is, first of all, in between A and B, on the board, so anywhere from here to here. And then also, that's the first point, and the second point is along the neutral axis on the cross section. And just for the sake of thoroughness, on mine I included, I said along NA on the cross section, which is 12.848 millimeters from the top. That way I was 100% clear about what region I was talking to. And that was just me saying where the location was, but that was the whole thing for part B. So that was that. Any questions on any of that stuff? Anything for this, using the equation, where negatives went? Dylan. They told us, note that the neutral axis is located 12.848 millimeters down. What do you mean? Oh, no, not on the y value, in the cross section. So I was just kind of describing location for them. So the first part of that location was, here's my length diagram. It's somewhere in here. Now let's turn 90 degrees. Look at it from the front of it, I guess you would say, from the cross section. And now I could tell you, in addition to being anywhere between A and B, it is also along the neutral axis cross section wise. The maximum stress is always along the neutral axis. They were asking for maximum shear stress. Maximum shear stress exists along the neutral axis. Yes. What was that? The tension? Oh, the thickness. Oh, okay. So the thickness, so on the same diagram that I was using to evaluate Q, where I did this line that I'm evaluating across, the thickness is just very simply whatever thickness it is at this height. Exactly. So along this line, what is the thickness here? So it was just the 350 millimeters across. Yeah, that's it. If you have anything else, you can come up afterwards, but good luck on the test, guys. Thanks, man. Yeah, just shoot me that whenever.
I will. Yeah, I think so. Peace.
Hey guys, quick thing wanted to add. I made an error in something that I said earlier. I just want to clarify something. From problem 3, when you're solving for Q, your moment of the area. So this is the cross section we were working with. You remember we shaded up to here. So the first part, that area was correct. It is just the area of the region you shaded. That y value you're evaluating now, that is the distance from the center, from the centroid of the shaded region down to the neutral axis. This is your y value. Earlier in the video, I know I mentioned that you're taking the y value from the center of the shaded area to the top of the figure. That's incorrect. You're measuring, your y value is the distance from that centroid to the neutral axis, or the line you're evaluating in that problem. For this case, it just so happened that the numbers turned out to be exactly the same, but for this one, just be careful in case you're not evaluating at the neutral axis and then it won't come out to the same thing. Just remember that this y value is actually the distance from the neutral axis to that centroid. Just wanted to clash that up. Sorry about that to everyone. Thanks again for coming out. Yeah.
Okay.
It was like,
good?
yeah, that's perfect. Thanks a lot, man. I appreciate it.
Totally. I love how you like looked around at the beginning to
Right, just like
pretend that you
there's
were.